In the next section, we'll look at this construction from Nisan and Wigderson to construct a specific pseudo-random generator, which seemed to do all the heavy lifting in this previous observation. That again, just to mention that, if we can get the construction in this section right, we have very strong evidence that BPP is the same as P. Again, the intuitive version first is assuming we have some Boolean function that has a high circuit lower bound, specifically this hard on average bound. The higher this function is, then the more pseudo-random bits we can pump out of this function from the same number of truly random seed bits. And so the overall construction actually works even in weaker state with weaker assumptions, where this hardness doesn't necessarily need to be exponential. If it's exponential, we get the full result that we used, and we can completely de-randomize BPP. There's also potential parallel universes in between, where we only know about somewhat weaker functions or somewhat weaker lower bounds on the circuit size of functions, and then we can still get something. My compromise for this section was to not show you the best possible construction for all these intermediate parallel universes, but rather focus on the most interesting case, namely that the full hypothesis is true and BPP can be completely de-randomized. I think it's also fair to mention that Avi Wigderson won the Turing Award 2 years back, among other things, for these kind of results. He certainly worked on many other things, but randomization and de-randomization are one of the things that were mentioned in the Laudatio. It again shows the kind of impact that these ideas had. Now, this section specifically, I think I'll exclude all the quantitative parts from the exam, just because it gets a bit too crazy and annoying to memorize. I don't think that's so helpful. And getting all the details right, I don't think adds much. The intuition and the qualitative ideas, I think, are fine. You should be able to get those reproduced, but not the setting of the parameters and all these bits. Just to state what in Aurora and Barak's book is the most sophisticated version of this result. So putting this into quantitative terms is what you get in this theorem. If you have any function where the average case hardness is S, then you could build from that a pseudo-random generator that gets almost S. But you have to take this some constant delta, where you take essentially the power to the delta in the end. So it makes it a little less than S of L, but reasonably close and good enough for our purposes. We'll not actually show this result in its generality. We'll show it, but only for the specific case of our exponential S. The key construction of Nisan-Wigderson's generator is actually surprisingly simple. And before going through the formal definition, let me just say, suppose you have seed bits, and you line them up. There's always going to be L seed bits in the parameters that we have. And we want to generate M output bits, which is many more, exponentially more. Then there's not so much you can do to get from L to essentially exponential in L. The only real construction you have at your disposal is take subsets. And maybe that's intuitive enough. So you take some subset of, how can I draw this nicer? You take some subset of these Let me try to do it maybe like this. That's going to get one output bit by applying our function f. That's the key idea. Then you take some other set that gets another bit, but again with function f. Now, this is going to go fine for some, but you're not going to be able to avoid overlapping sets if you want an exponential size down here. Right? There's not enough bits in L. So we'll have potentially overlapping subsets. And we'll take a whole family of subsets of the positions in L. And we'll just output all of these, the sequence of all of these subsets. So take the appropriate indices in the subset and feed that to your hard function f. And that's your sequence of pseudo-random bits. I think after seeing it, it's almost like how else would you do it? It seems like almost the only way that could potentially work. But of course, the crucial ingredient here is this this subset, this collection of subsets. And also, we somehow need to show that by doing this computation with overlapping sets, we don't make the result too predictable. Otherwise, it wouldn't be pseudo-random. So that step is maybe very natural, but the magic comes in the following steps. And the key definition, how they came up with this, is not clear to me. The key definition is to have the right restrictions on these subsets to make everything tick. The general framework is, well, they called it combinatorial design, which is a very non-telling term. It's just a collection of subsets from a set of size L, the seed bits. Each of the sets should have size n. In total, we want m of these subsets, and we want to use a very large m. And then there's a third parameter, which is d, and that's the bound on the intersections. So any two of these subsets should have at most d positions in common from the in total n. And in general, it only makes sense if d is at most n, obviously, and n is at most l, obviously. But we'll need some slack between those numbers for such a thing to exist. So this is just the definition that says if I have a collection of subsets satisfying these properties, then I call it a combinatorial design. But you can easily pick parameters for L, N, and D where no such thing exists. And so with this, we're skating at the boundary of existence. And the concrete set of parameters that always works are in this lemma. This is both existence, but also an algorithm to compute such a design. And it's a lovely kind of, it's ironic that the algorithm itself uses de-randomization, but is based on a probabilistic method proof. That's somehow, this could be from Gödel-Escherbach. Okay, forget it. Maybe you'll follow the joke after the proof. So we're given the parameters n, l, and d as input, and we're supposed to generate all these subsets. Because the output is so big, it's definitely going to take a while. Okay, so we allow ourselves exponential time in L. That's fine. At the very end of the game, L will be logarithmic, so no reason to worry. And the restrictions are that L needs to be substantially bigger than n, and the size, the number of outputs, the number of sets in our output set that was called m before, is 2 to the d over 10. Again, these constants you can probably play with, but no need to. What you don't yet know, or what you cannot yet see, is that these sets of parameters will make for a suitable pseudo-random generator. That's for tomorrow. But I want to briefly show how to do this construction. The algorithm is incredibly simple. We start with no sets, and then we are bluntly iterating over all possible subsets, and we pick the first that we can add to our set without violating any constraints. And the constraint that's relevant is essentially the intersection constraint. If I already have built a collection of some subsets in my calligraphic eye, then if I take a new subset, it might have too many indices in common with some previous set. But I'm going to allow myself to run through all possible subsets. I have exponential time, so why not? And the first one that has a small enough intersection with all previous sets, I'm going to take. So the only question, this algorithm is obviously correct in that it never produces an output that is not a combinatorial design. But the key is it possible that this algorithm finds enough sets? Why could it not possibly be running into a dead end and be stuck so that no set can be added, but we don't have the number of sets that we wanted? So the thing that we still need to show is that A always succeeds. And look at the algorithm, that there's no randomness, okay? It's deterministic. It just does essentially a brute force approach. But to prove that it works, we'll use the probabilistic method. And I've only vaguely explained what that is before. So this is a good way to show you what it does in action. We'll just, instead of running the actual algorithm, instead of going over all subsets, what we'll do is we generate a set at random and show that the probability that this succeeds is not 0. And that's the probabilistic method. That's all it does, really. If you have something to generate, and there's a probability that the random object you build is that object, and the probability is greater than 0, then such an object exists. Otherwise, the probability had to be exactly 0. And here we have some freedom. We pick this random set for each position in the allowable indices. We pick the position with probability 2n divided by L. So on average, we'll have 2 times n elements in the set, but it's also random how many, right? But we make the set, we bias the set to be a bit bigger than we need it. And then this is kind of exercise level, and I'm skipping the math this time. You can show with the standard Chernoff bound, because these are independent and with the same probability. These are just binomial random variables. These involved sizes. The probability that the set that you pick is way too small is very small. At least if n is big enough, certainly this is true, because you're expecting way more. You expect 2n. So half of that you'll most of the time have. And also for any fixed set that you already have, the probability that you have a larger intersection with that set than D is exponentially small. And that comes from this bound on L. So in a way, L is so huge that if you only pick 2n of the positions, and here and there, the fact that many of them overlap is actually not likely. Now that's for one specific set J. In the end, our set capital I, or calligraphic I, will have a lot of these sets. And we want that we don't have a large intersection with any of them. So this is the bad event, that we have large intersection. The union of all those bad events is that any of the events, at least one bad thing happens. So we can use the union bound on this. We do the probability that I and a specific J have large intersection. And so we take the union over all J in our calligraphic I. And that's where we use the union bound. It's the size of I times the probability for this, and that's the 1/2 to the minus d over 10. And then if you plug that in, this guy is less or equal to the d over 10. That part just cancels and you get the 1/2 that we have here. So the probability that the new set does not intersect any of the sets at too many positions is at least 1/2. And if you take the two together, we want both of the good things at the same time. We at least have a probability of 0.45 that the new random set is good, that in the sense that it has a small number of intersections with everything before and is large enough. Now it might be too large, but that's actually, you can just remove some of the positions until you're down to size n. That can never add intersections, and then you're done. So the beauty why this analysis here is so easy is that because you're picking things independent and at random, you establish exact and complete symmetry on this universe L, so that it doesn't matter what the current sets look like. You can upper bound the probability to intersect any of them in the same way. So in each of the steps where we add a new set, we have some fixed probability to succeed. Now we need to succeed in every round. So actually the probability for m successes in a row is tiny, but it is non-zero. And so some choice exists for the algorithm to pick, and it'll just find it by brute force. Okay, so that's the probabilistic method in action. Although we're analyzing a non-probabilistic algorithm for a key ingredient in building a pseudo-random generator for de-randomizing algorithms. Cool.